So today we're going to explore the fabulous world of vectors. Now, many students hope that vectors, you get them with, you do that, and you never have to worry about them again. Well, that's not true. The idea of vectors will keep coming back in physics over and over again. If you go on to take linear algebra at the university level, they will talk about vectors in a slightly different way, but after a couple of years, you'll realize that they're kind of one and the same thing, just sort of looked at a little bit different. Okay? We're going to start with the idea of vectors as being geometric, which is why I should have asked you yesterday to bring a ruler, and I was yelling at people before class that if you have one in your locker, you'll get it. I have a few spares, so we should be okay. So we're going to be dealing with them on in grade 11 as sort of geometric kind of figures, and then in grade 12 I'll show you how to deal with them sort of on a more mathematical way, and you'll say, why didn't you show it to us that way last year? Because you got to be able to understand sort of the basics. So we're really going back to I'm almost teaching you basic arithmetic, okay, in the idea of vector. So after today, you'll know what a vector is, understand vector direction conventions, and be able to draw a scale drawing of a vector. And there's an example of a vector on the page right there. Do you have that on yours? You don't need to worry about that. Just a pictorial representation. Okay, so what is a vector? Well, in simplistic terms, a vector is an arrow that represents a vector quantity, which isn't really very explanatory. Doesn't explain a whole lot, right? A vector is an arrow that represents a vector quantity. So then the question becomes, what then is a vector quantity? Well, we'll get to that. The length of the arrow, how long it is, represents the magnitude or size of the vector. Now, I often get kids ask me about the word magnitude later. They don't remember this part, so I'm going to ask you to highlight it or do something to remember it. Magnitude means the size, how big it is. The longer the vector, the bigger the vector quantity. Okay? When we were talking about models, a scientific model is something that's physical that represents something that you can't really see. A vector, an arrow, is really a good example of that. It represents something that we can't really see. A force could be a vector, and you can't really see a force, but you can represent it with an arrow. The length of the arrow represents the magnitude or size of the vector. That's what you have to write down, right? And that the direction that the arrow points represents the direction of the vector quantity. If a force is in a certain direction, then that can be represented on paper by the direction of the arrow is pointing. This arrow is pointing to the right. This force, or whatever it is to the right. It's pretty simple, right? I'm just sort of defining for you. Quite often the definition is confusing because it's so simple you're like, well, of course. Vector quantities are quantities that have a direction associated with them. If you can put the word north or right or east or down after it, then it will be a vector. Quantities that have a direction associated with them. I'll give you some examples. I think that's next, right? Common examples are, these are the big four I call them. Displacement, velocity, acceleration, and force. Those are the big four when it comes to vectors. Displacement is how far you've gone in what direction. I walked 1, 2, 3, 4, 5 steps to the right. That's my displacement. To the right. My velocity, I'm traveling at 100 kilometers an hour south. Acceleration, minus 9.8 meters per second squared down. A force of 200 newtons to the right. Anytime there is a direction, it is a vector. The opposite of vector is scalar. Are you with me, ladies? Opposite of vectors is scalars. They are quantities that do not have a direction associated with them. Things like mass, 100 kilograms, time, 6 hours, cost, $4. You can't say, how much did that car cost? $10,000 south. It doesn't make sense. Things that you can't put a direction at the end are called scalars. Okay? And up to now, almost every quantity, everything that you measured, everything you talked about was a scalar. And so now we've expanded your horizons a little bit. Okay? And again, we'll be dealing with these in a sort of geometric sense. Should we watch this one? Sure, why not? On your own. Okay, so I have given you a definition for a vector, and I told you what a scalar is, and I gave you the big four. So now I'm asking you to think of it. Which of the following properties in physics do you think is a vector? In other words, what is a vector? It has to have a direction associated with it, right? So which one of those would classify also as a vector? Would it be speed, density, momentum, or volume? And hopefully you've got at least one clicker per table. It's not for marks, it's for learning. That's the real reason we're here. Oh, I got one that's working now. Who needs one? No, nothing more. Sometimes if you turn it off. I'm waiting on two people. Cameron, what do you think? A, B, C, or D? Okay, and the answer is C, momentum, not speed. Had you been paying attention, instead of on your phone during the football video, they talked about speed of the receiver, I think, right? Then they talked about the velocity, which is speed plus a direction. So speed is the scalar version, velocity is the vector version. So the correct answer, and it's not density because grams per cubic centimeter south doesn't make sense. Momentum is in a certain direction. The linebacker has a certain amount of momentum as they move downfield. That makes sense. Not volume. Say again? That's true. And momentum is a quantity of mass and velocity. Right? So it is the vector, yeah. And again, not a big deal if you didn't get it right. Not a big deal. Okay, so here's a chance to redeem yourself. Which of the following do you think is a scalar? And remembering that scalars have no direction associated with them. Scalars have no direction. Kind of like my life at times. Are you guys, is your whole class going to be in, Caleb, do you think? No? Okay. Okay, so which of the following do you think is a scalar? Is it gravitational field strength, is it density, magnetic field strength, or torque? And I realize that some of you may not be that familiar with all of those. I'm just making you think a little bit here. Which one doesn't have a direction? Is that one not working? And the correct answer is B. Well done. In fact, I think I mentioned that in just the previous question, did I not? Did I not say density, grams per cubic centimeter doesn't make sense to have a direction? Paying attention will work wonders for you in here. Really does, Anna. Okay, back to the notes. So, algebraically, vectors are represented by a variable with an arrow over it. Okay? When you draw a vector, when you do an algebra, or if it's in a textbook and they're talking about vectors, they will draw a letter, they will have a letter with a little tiny arrow over top of it. That indicates that it is a vector. For now. Don't worry, don't sign out. There's more coming. Guess what? I'll do some teaching, and then I'll do some checking to see if you've been listening. So, you can put a vector over, or an arrow over like that. Most of the time when we're handwriting them, we only put a half of the arrowhead, just for simplicity. Okay? In the good old days, before computers and desktop publishing, to show a vector in a textbook, they would usually put it in italics and bold, and then putting that little arrow over top was actually quite challenging. Okay? Now you don't see that too much. If you had a really old textbook, you might see that. But if you see that with the arrow over top, that means that it is a vector. Now, the next statement here is kind of self-explanatory. It's almost one of those things that's so simple it doesn't really need to be said, but I need to say it. When representing a vector graphically, you can move the vector anywhere you like as long as the length and the direction which it points remains the same. So as long as the length is the same and the direction that it points is the same, they are identical vectors. They're equivalent. For example, the two vectors shown below are considered equal even though they don't have the same starting point. So those two arrows, do you have them on your page? No? They would be equal as long as the length is the same and they point in the same direction, even though they're not at the same place on the page. Okay? It's the same idea. Have you ever thought about this? Is that equivalent to that? They're the same number. They mean 2, right? Even though one's in black, one's in red, one's written a little bit differently, and they're in 2 different spots. It's hard to believe they mean the same thing. Right? So same idea. As long as they represent the same thing. These vectors represent the same thing. They're in the same direction. They're the same length. They're the same. Okay. Now, you may have been starting to wonder, because maybe units mean a lot to you. And units are important, right? Vinny, how'd you like 5? How'd you like 5? 5. How would you like me to give you 5? Exactly. If it was $5, he'd say sure. If it was 5 smacks in the head, not so much, thanks. Units are important. Use them on tests. The unit of magnitude of a vector depends on the type of vector you're representing. For example, a displacement vector would be measured in meters, because that's what you measure displacement in. What I'm getting at here is there is no special unit for vectors. Vectors are a category of quantities. Okay, so displacements are measured in meters. Skylar, do me a favor. Vectors are simply a category of units that have a direction. Okay, let's get down to the nitty-gritty here. Let's talk about vector direction. There are multiple ways to indicate direction. You need to be multilingual. Some of you speak more than English. That's great. Some of you don't. It's better to speak more than one language. It's good for your brain. It's also good to be able to talk about different directions in vectors. I'll give you the simplest one there is. For example, as a man is following the lamest scavenger hunt ever devised, he used to walk plus 35 meters and then minus 10 meters. Boring. The plus indicates what? Forward. The negative indicates backwards. That's a standard convention. When I say convention, I mean it's something that we all agree upon, right? Plus is forward, negative is backwards. Okay, so that's one way to describe direction. And it's actually pretty useful in pretty much all of our, most of our sessions, most of our examples, I guess you could say. Okay, here's where it starts to get hard. If you've been tuning out, going, yeah, well, whatever, it's not that hard. Here's where you got to start paying attention. Airplane is traveling at 200 kilometers an hour at 40 degrees south of east. Okay, well, before we even get into that, let's just remind you that north is always up, and then we have east, south, west. Never eat soggy wieners. Little tip for you, right? When you watch the 6 o'clock news, that is information that comes from all directions, is it not? And that's why they call it the right, Anna? Did you ever think of that? Did you know that? I'm probably just making that up. I don't know, actually. I've been saying that for so many years, I don't even remember if it's true. You can look it up. It is kind of weird, eh? Okay, 40 degrees south of east. The order matters. South of east. So you have to look which direction first. South of east. So you're looking east and then going 40 degrees towards the south. 40 degrees south of east. Okay, that's one way to describe it. Now there's another way to describe it, and that's written like this. E40S. E40S means look east and then go 40 south. Now in my experience, most students prefer this method, east 40 south, because it kind of like it's that order, right? You look east, you go 40 degrees towards the south. Keep it all in order. They don't like 40 degrees south of east. But you got to be able to deal with it if you have to, okay? 40 degrees south of east. What kind of objects might travel at 40 degrees south of east? Like, who would have to know that? Who in their right mind cares about this? Pilots that navigate. People that are navigating on boats need to be able to do this. Okay? Okay, get the clickers out. Hopefully you've been paying close attention. And now the question is, which of these arrows shows the direction 30 degrees north of east? North of east. There's only two options, so I've made it pretty simple. Limited your choices. Raphael, the answer? A or B? 30 degrees north of east. Or if you prefer, east 30 north. Most of you got it. East 30 north. Look east, go 30 north. Okay? You got to be able to do this because the next step is going to get harder. I'm going to build on this, right? So you got to get this. 30 degrees north of east. You start with this one, go 30 degrees to the north. Okay. The last convention. This is the one that actual pilots actually use, because if you're piloting a plane, you're the navigator, and the traffic controller says you need to make a heading of 40 degrees south of east. You can't be flying your plane going east. You can't be doing that, right? You gotta be quick. Okay? So they use this bearing method. A sailboat is moving at a bearing of 210. I put my bearings in the square bracket. If you see that, it means bearing. Okay? This method assumes that 0, 0, 0 is north and it revolves clockwise. So go back to the news. The top is 0, 0, 0. North is 0. And it revolves clockwise. Now, in today's digital age, clockwise might be foreign to you. You know, this kind of clock. Which way is clockwise? That, right? Wipe on. Not to wipe off. Wipe on. You know that movie? Anybody seen that movie? It's like from the 80s. So, east is going to be 90. South is going to be 180. And west is going to be 270. Now, interesting little tidbit of useless information. The mathematicians do this. Don't write this down. They go 0 over here, 90, 180, oops, 270. They start 0 at east and they go counterclockwise. That's what they do in math class. Have you seen that yet? Unit circle. Has anyone got to unit circle yet? Isn't the unit circle fun, Jason? No, you don't. No one in their right mind likes unit circle. Even the unit circle, like I like math, the unit circle sucks. Okay, when you get to that, that's just in math. Real pilots, real navigators use this. In fact, if you're flying on a plane Look out the window as you're approaching the runway, and the number of the runway will be the direction that you're facing. Did you know that? So if you are on runway 27, it's because you are flying west. When you're landing on runway 27, it's because you're flying west. They just chop off the last number because they go in like multiples of 10. Interestingly enough, if you're flying the other way on that same runway, you're going to be landing on runway 9. If you're going this way, it's runway 9. If you're going, I guess, yeah, this way it's runway 9, that way it's runway 27, depending on which way you're coming from. You will actually see the numbers there when you land and take off. You have to look carefully because it happens pretty quick. Don't you think it'd be really cool? You know that like in-stream on the plane where you can see the map where you are in the world? You see all that? Don't you think it'd be cool if they had like a camera in the nose of the plane that you could actually watch as you're flying ahead? Wouldn't that be cool? I keep suggesting that to WestJet. They haven't done that. Okay. So now that I've given you the instruction, I've given you what you need to know, tell me, which one of these is vector direction 300? Which one is vector 300? Alexis, did you press enter? And the answer is D. Well done. D, because, remember, 270, right? So that's going to be like that. Now, if you had direction 300, how would you convert that? How would you translate that to the other version? 300 would be equivalent to what? 30? No, I don't mean the runway thing. I mean like the east, south, west, all that. It'd be north of west. So it would be, how many degrees in it? 30. 30 degrees north of west is correct. Or alternately, that would be west 30 north. You see how they all fit together? Okay? Awesome. Oh yeah, almost done. Scale drawings are often used to represent vector geometry. Have you guys done scale drawings like in math, maybe like grade 5 or 6 or something like that? Maybe like drew a house or something like to scale or something like that? No? Never did that? Oh, a long time ago? I remember doing it. For example, a vector of 300 newtons east. How would I show 300 newtons east? Well, first of all, the arrow has to be pointing east. But how long do you make it? Now, I don't think I have anything here. I think I have to actually do it here. How do you make 300 newtons east? The first thing you need, because it's a scale drawing, you need a scale. So you start your scale with 1 centimeter equals. Now, I have to pause here, because about half of you, now maybe a quarter of you will get this wrong on the test. You always start the scale with 1 centimeter equals. The first thing in the scale talks about what it is on the paper. So we're going to say 1 centimeter equals, and then pick a number. Like 14 is a bad choice. 10 newtons. You want something that goes nicely into 300, right? 10 is going to mean that I'm going to need a vector that's 30 centimeters long. That's pretty big. You can go 100. Let's kind of make it somewhere in the middle. Let's go with 50. Long enough that it's not too tiny, you can't see it, but not so big that it falls off the page. You know why 14 is a bad choice? Was that you, Trent? You know why 14 is a bad choice? It doesn't look nice. Will it work? Absolutely. It's just kind of odd. Okay? Yeah. So 1 centimeter equals 50 newtons. So now I'm going to draw an arrow that is, and you get your ruler, and I have rulers here right away. Okay? You're going to draw an arrow that is 6 centimeters. How did you get the 6? 300 divided by 50. So 6 centimeters to the east.
Okay? Don't worry about it if it's a ruler just yet. If you don't have a ruler right now, I'll get you one. Don't worry about it. Okay? So that's sort of a simple one. But now you also have to do it with direction in there, as I told you. Okay? I'm sort of adding on stuff here, right? Adding on some knowledge. Okay, so here are 4 to try. I have some rulers here. If you have your own, that would be great. Please return these rulers if you borrow. I realize that many of you don't walk around with a protractor in your pocket like I do. No, I don't actually do that. Where is that? Oh, there it is. I have some protractors here for you to cut up, and I just realized I don't have the scissors in here. Okay? Now, I have these kind of protractors. They are the full 360 kind. Most kids don't mind these ones because you can do the whole like 360 kind of thing. Some of you don't like them because it's not what you're familiar with. Some of you just prefer the half circle one. So come and pick whichever one you want. If you have your own protractor, that's great. I'm going to get some scissors. Might need to share scissors and such. So by the end of this period, you got about 12, 13 minutes. You need to have a ruler, protractor, and try at least 2 or 3 of these.
So should I bring my protractor so you can class?
For the next little while, we're going to use it.
Okay, I'll bring it.
If you have one at home, drag it out, bring it there. I got these little cheap ones here that you can use. If you borrow a cheap one here, stick it in your binder where you're not going to lose it, because I don't have tons to hand out. Like I can't give you one every day. Okay, so then this is going to be, whoops, that arrow is going to be 5 centimeters long.